Hello everybody, this is the last lecture for our gas law chapter, and I'm going to cram in a bunch of random topics that didn't warrant their very own PowerPoint and weren't really covered in other places, or things I want to give you one more reminder about into this kind of a hodgepodge of a lesson. So let's get started with gas density. You did learn a little bit about this already. I just want to remind you about it. That remember the density is mass over volume, so we can use that to perform a variety of substitutions into our ideal gas law equations. And then also, if you think about it, if it's at STP, which it often is, the molar volume would be 22.4 liters. So when you're at STP, if you can remember that 1 mole of gas occupies 22.4 liters, you can make this an even further shortcut to help you with some of those calculations you might find. It's not that you couldn't do separate calculations to get your volume, but you can save a lot of time using that as a shortcut. Remember we learned about molar mass, kitty. We have our density, which we can rearrange. And we remember it with that ridiculous little cartoon. Molar mass kitty puts dirt over its pee. Next, way back at the very beginning of the school year, you did see the equation for kinetic energy. One thing that's really important is that you understand that we're measuring the average kinetic energy, not necessarily the speed of one particular molecule or a particular atom. We don't often do calculations with this, but it is a good reminder that you can use the mass to give you some, insight into which particles might be moving faster versus slower. Which ones would have higher or lower kinetic energy, things like that. A reminder that temperature, when we use Kelvin, right, is a measurement of the motions of the gas particles. It is giving you an idea about how much motion there is. So a higher temperature means greater motion. We have more of that kinetic energy. So our average kinetic energy can be related to this equation sometimes as well. Once again, not necessarily something that we will be using a lot, but I just want to throw it out there in case you stumble across it. Next is the concept of diffusion and effusion. They sound similar, and they are a little bit similar, so be careful that you don't mix them up. Diffusion is what we get when gases are mixing with each other. So we have two containers here of separate gases. We remove the divider, and we see how they mix. The rate of diffusion is how quickly these gases will mix with each other. And if you think about it, we see diffusion in everyday life. Say you're in the classroom and somebody opens a jar of like a strong perfume or something. In the beginning, if you're in the other corner, you won't smell it, but over enough time, the particles will diffuse, they'll mix together, they spread out, and you end up smelling it eventually. Effusion is a little bit different. Effusion is talking about how quickly can a gas go through a tiny little pinhole into a vacuum. So it's not about gases mixing together. Effusion is that you have one gas in a container, teeny tiny little hole, and how quickly will that vacuum get filled with gas particles. I like this picture because I like that these show you we have like a big separation here in the divider, or you completely remove the divider versus the tiny little hole. And with diffusion, they'll kind of mix in both directions all together. With effusion, one side is completely empty, and so these gas particles will go through that little hole and start to fill up that vacuum. We can do some calculations to measure the rate of these things. We use Graham's law, and we're often not measuring it directly with very specific numbers. We're usually just taking ratios of one gas compared to the other. We are trying to figure out how much faster or slower would one gas be versus another. So the rate of effusion for gas 1, how quickly can gas 1 go through that teeny tiny little pinprick, compared to how quickly can gas 2 go through that teeny tiny little pinprick, is going to be the ratio of the square root of molar mass. But you need to look very carefully at this equation. This is a gas 1 over gas 2, but over here, it's the square root of molar mass 2 over molar mass 1. Be very, very, very careful about that. For diffusion, it's very similar. It's basically set up the same, but instead of the speed at which it's happening, we actually will use the distance that the gases travel. And a reminder that our capital M is molar mass. We are not going to get into any of the derivations of this. We are not going to stress out and worry about, why are they in the order they're in, or why do we do rate versus the distance. Don't stress about that. Usually the data they're going to give you is going to be in the number of seconds it takes instead of the distance, so they're not even consistent with the equations that they use even. Just use the number in the data they give you. Sometimes what they will tell you is that if you have gas number 1, it travels 4 times faster than gas 2. What they're telling you is this part here. If gas 1 is 4 times faster, then what you would put for this ratio would be a 4. If it was 1/2 the speed, you'd put a 1/2. If it was 10 times faster, you'd put a 10. And then a reminder once more, be very careful that you notice that it's 1 over 2 and then 2 over 1. Be very careful about that. If you stop and think about it, you should realize that the lighter particles can go much faster than the heavier particles. So the smaller something is, the faster it will go. That inverse relationship is why we're getting this upside down order here. Let's do a practice problem. Under the same conditions of temperature and pressure, does hydrogen iodide or ammonium effuse faster? Calculate the relative rates at which they effuse. So we're going to set it up where we know that NH3 will go faster. And I suggest, if possible, if they leave it open-ended, put the smaller molar mass as gas 1. That way you're always seeing how much faster things go. Bigger numbers are usually easier for us than dealing with fractions, right? Of how much slower something is. So if I want to see how much faster NH3 is, I will set it up with the square root of the other thing, the hydrogen iodide on top, and the NH3 on the bottom. So you can see Here's the molar mass of hydrogen iodide. Here's the molar mass of ammonia. Square root those things, and you have seen that ammonia is 2.74 times faster at effusing than hydrogen iodide. It will fill that container, go through that tiny little pinprick 2.74 times faster. So when they're asking for the relative rates, be careful, don't just give this number at the end, okay? Write a little sentence that says, NH3 2.74 times faster than HI. Once again, kind of like when we were doing atomic structure stuff, periodic trends, if they're asking you to compare two things, make sure you mention both substances. Don't just give a random number, okay? The next kind of random thing to throw into this PowerPoint is I just want to show you one more time about the correction values if we're dealing with real gases instead of ideal gases. Not that I'm asking you to use this equation, but I think understanding the equation helps you remember the differences between real and ideal gas. If something was ideal, it would have no attractive or repulsive forces between particles. They would ignore each other. The pressure would be perfect. They would also have no volume. The gas particles would be individual point particles with a volume of 0. They would have no volume that they took up themselves. But in real life, every single atom takes up space. So if we look, we have to correct our pressure and we have to correct our volume. If you notice, we're going to have a fixed pressure where we take into account any of the attractive or repulsive forces. If they're attracted to each other, like maybe they're polar. If they're polar, they're going to be drawn towards each other, right? Then you'll have less collisions. And then your volume needs to be corrected by taking out how much space those particles themselves are occupying. And that is how we can correct our ideal gas law equation. Here's another little thing that pops up sometimes. Oops, typo. Let me fix that at the top. There we go. Okay. Sometimes they'll ask you to calculate the root mean square velocity, and to be perfectly honest, I think since most people haven't taken physics, this is a little bit silly to do, but it pops up every once in a while, especially in older questions. I don't suggest you skip old questions, right? But, maybe flip and look at the equation in your notebook. One of the things that's important is it's a good practice to make sure that your units are matching. Your R value being in joules requires that your molar mass be in kilograms, which can really throw some people off. So it's a good way to make sure you're paying attention to those units. The next thing is something called gas stoichiometry. And gas stoichiometry, to be perfectly honest, is not really anything different than regular stoichiometry. Regular conversions. Instead of using a regular conversion factor, you might be using ideal gas law instead. Maybe you have to solve for volume using ideal gas law, or using molar volume if you're at STP. I have had very good luck over the years not teaching this as a totally separate topic. I don't teach this like it's its own separate thing. I like to point out we are still doing stoichiometry. You still have a pathway to follow. You still cancel your units. You're still doing that. You just have a different way to get from point to point. And I hope that can help simplify it for you. I would like to do a couple gas stoichiometry problems in the lecture right now because sometimes there's not enough time in Honors Chem to do these. So just a real quick reminder for some of you. We'll do those in a sec. One thing first is to understand that if you have the same temperature and pressure, your mole ratio can be used as volume ratios. So you're used to thinking of these equations as a 3:1:2 ratio in terms of moles, but you could also do it in terms of liters, because each gas will occupy the same amount of space under the same conditions if it's the same number of moles. So if you have 3 times the number of moles, you would have 3 times the number of liters. If you had 2 times the number of moles, you would have 2 times the number of liters. That can be a very helpful shortcut to use. So, how many liters of ammonia can be produced when 12 liters of hydrogen react with an excess of nitrogen? I'm going to start with my known value. And just like I would use a mole ratio, I am going to use liters. I'm trying to cancel the hydrogen so it goes on the bottom. Ammonia goes on the top. And then I look at my coefficients. I have 3 liters of hydrogen for every 2 liters of ammonia. So I cancel my units, and I see that I get 8 liters of ammonia if I start with 12 liters of hydrogen. I'm hoping you can see that this is still dimensional analysis, isn't it? You learned this in the first week of honors chemistry. That might have been a really long time ago, but you've been practicing dimensional analysis for literally 2 years now, haven't you? Year and a half, but close enough, right? This conversion factor is just one you're not used to, but the process is the same. All right, how many liters of oxygen gas at STP can be collected from the complete decomposition of 50 grams of potassium chlorate? So here's potassium chlorate breaking apart into potassium chloride and oxygen gas. I have good neutral formulas. I've balanced it. I'm going to go from grams of potassium chlorate to moles of potassium chlorate. Then I can go moles of oxygen gas. And then finally I can go to liters. So I'm going to go from grams of A to moles of A, moles of A to moles of B, moles of B to liters of B. If you had me for honors chem, that little sing-song rhyme I just did makes sense. If not, talk to me about it or watch one of my old honors chem lectures. Okay. So here's grams of my starting value. Grams to moles uses molar mass, which I get from the periodic table. Moles of one thing to moles of the other, moles of A to moles of B, is going to use mole ratio. The coefficient in front of potassium chlorate is going to go on the bottom. So they cancel, and the coefficient in front of oxygen gas will go on the top. Now, if I was not at STP, I would have to get an answer and plug that answer into ideal gas law. But since I'm at STP, I'm really, really happy. I can just add one more conversion factor, which is that at STP, 1 mole of any gas will occupy 22.4 liters. I punch all of that in my calculator. I'm careful with my parentheses, and I find out that when 50 grams of potassium chlorate decomposes, the gas that gets made will occupy 13.7 liters. That's how much space it will take up. Here's one that's not at STP. So like I said, you're going to need to figure out how many moles you have, and then you plug it into ideal gas law. You're still using your mole highway. You're just going to use ideal gas law at the end. Why don't you pause the video and see if you can do this problem start to finish. All right, here we go. I'm going to go grams of A to moles of A using molar mass, moles of A to moles of B using mole ratio, and now I know how many moles I have. I'm going to take that answer and I'm going to plug it into the ideal gas law. You may like to rearrange your equation before you start. I am personally too lazy for that. I always just plug it in and then rearrange. It does not matter which way you do it. Make sure that you're using the correct R value to match your pressure units. Make sure your temperature is in Kelvin, not Celsius, and you get your final answer. Now this should make sense, right? Yeah, the pressure's a little bit lower, so it should take up a little more space. And that temperature's a lot higher, isn't it? It should take up even more space. So even though it was the same number of grams, even though we were making the same quantity in terms of the number of moles, the number of grams of oxygen gas, it'll fill up a larger container because of the lower pressure and because of the higher temperature. Always, always double check if your answer makes conceptual sense. You can find a lot of calculator mistakes that way. Last little reminder, a throwback to the very first one about the concepts, because everybody forgets to think about these. Please study these also. Remember that gases behave according to the kinetic molecular theory. And the idea behind this theory is that the particles are always moving. And thinking about how the particles move and thinking about how they behave explains everything. Okay. If you're stuck, think about particle diagrams. Think about how the particles are moving. Remember that pressure is caused by those collisions with the container walls. More collisions, more pressure. Remember that your average kinetic energy is proportional to your temperature if you're in kelvins. That's why Kelvin's so special, right? Absolute zero means no motion. And then remember that this is all based on assuming we have perfect ideal gases with no volume and no attraction or repulsion between those particles. I know that honors and AP students are so good at math, which is awesome, but that's why they're going to make a point to ask you some concept questions too. They need to see that you understand the math you're doing, that you understand the science behind the math. Okay? That is it. I hope that was helpful. Bye, everybody.